Hello! I'd like to talk about performance laws, and true to the clickbaity title, we're gonna embark on the journey to discover the silver bullet of performance, how to make things harder, faster, and better. Okay, I know there is no such thing as silver bullet. Well, unless we're talking about Amdahl's law, right? Not really. I'm not even considering it a law because it doesn't seem to describe reality that well. In fact, I'm pretty sure that if you worked with distributed systems or parallel systems, you notice that as soon as the number of nodes reaches certain threshold, performance not only no longer gets better, it actually drops, which is unfortunate. That's why Gunter's universal scalability law is better in this regard because it takes into account the communication overhead, but still it's not very constructive. Meaning we cannot really use it to devise better algorithms. It's more about, I guess, emphasizing the limitations of existing approaches. So, what can possibly be better? And to see what we can find, we can try using Lindy effect, which basically means that all things tend to get stay tend to stay longer with us. And since computer science is a fairly new um, science, we are gonna go all the way back to the mathematical roots, and we're gonna start with such small things as just a bunch of objects that can be in a set, and we can potentially have multiple sets. And as soon as we have multiple sets, we can start adding some relations between these objects. And what relations are essentially are a bunch of pairs of objects from one set and another set. Or in other words, it's a subset of the Cartesian product. And since it's a bit tedious to describe all these pairs all the time, we, as programmers especially, like to use functional notation, which essentially creates a relation between the inputs from one set and outputs in another set. And this way, we get a concise notation. Obviously, it's not as powerful as an entire relation because functions map only one input to one output, whereas relations can technically have multiple outputs. But it's pretty good for our purposes. And now that we have defined relations, I highly recommend you watching the talk by Sean Parent called Better Code Relationships. In fact, I recommend watching all of his amazing talks. There is no way you won't learn something new from each of the talks. They are really great, and I'm super excited to have Sean part of the event. Now that we have relations, we can talk about their properties, and one of the first ones is associativity, which basically means that we can apply our operator any way we want. Or put in another way is we can parenthesize the expression in any valid way. Um, how useful could that be, right? Well, first, let's see that it doesn't always work as expected. For example, in JavaScript, plus operator is not associative for floating point numbers, which is a bummer. So now that we know what we don't have in JavaScript, you can talk about like why do we care? And for example, we can use associativity for parallel reduction. So instead of applying the operator one by one, we can actually conduct essentially kind of like a tournament with elimination where we pair two arguments, apply an operator, and this way we eliminate half of the inputs on every step. So this way we can get logarithmic performance instead of linear as long as we have enough computational resources. We can also use them to snapshot our data in event sourcing architecture, which is super useful for both reliability and performance. It's also very useful for matrix multiplication, especially when it comes to matrix chain multiplication, because in terms of denotational semantics, it doesn't really matter in which order we apply multiplication operator, but operationally there is a big difference. And even for small matrices, as on this example, we can see that multiplying AB then C results in 108 operations, whereas multiplying A to B and C results in 400 operations, which is clearly much less efficient. And we can see it in practice. So for example, when we measure the runtime of both function multiplications, we can see a significant difference. And that's why there is a beautiful dynamic programming algorithm that allows us to compute the optimal multiplication ordering. This associativity property is also a key to such data structures as segment trees, which allows us to pre-compute values for subtrees and then combine them to efficiently return results for queries, and also support efficient modifications. So both are logarithmic. And if we also have a distributivity property, we can even optimize it further by doing lazy propagation, which improves modification performance. We can also define inverse function, which basically means that not only we can go from inputs to outputs, but we can also go from outputs to inputs. And once we have this property, we can use prefix sums, for example, because we can compute the sum of the range, but to compute this subrange sum, we need to subtract, and subtraction is an inverse of the addition for integer numbers. And this way we have constant time queries, and unfortunately we don't have efficient modification support, but we do get linear space, so it's very simple to implement and very fast in practice, and it also supports two-dimensional data structures. If we do need to support modifications, we can use Fenwick or big trees that support both queries and modifications in logarithmic time. And now we have all the ingredients to define the first mathematical object called a semigroup, which is pretty much just a set of objects and a binary operator that is associative. And in Haskell, it looks like this. And this less than, greater than is a notation for the binary operator of the semigroup, which is also sometimes called concatenation. And unfortunately, even Haskell doesn't have enough expressivity to encode the associativity property. So it is still something that developers have to prove on their own. But you may have noticed that we have these extra functions called sconcat and stimes. And even though those functions are not really required for the semigroup, they are super handy. That's why they are there, especially the stimes one, because it's essentially the fast exponentiation function that makes it possible for us to raise values to the power of n in log n time instead of linear time, which is very handy when we, for example, want to compute Fibonacci numbers, because multiplication of such matrices is associative, so we can compute Fibonacci numbers in logarithmic time. And yes, there is a way to compute Fibonacci numbers in constant time, but that's a topic of another discussion. And we can see that in practice it does make a difference whether we use matrix multiplication, tail recursive implementation, or recursive implementation. The numbers differ pretty significantly, so I highly recommend checking out if your operations are associative. And probably nobody has leveraged mathematics in computing setting more than Alexander Stepanov. who has introduced a concept of generic programming. And even though a lot of people think that it has something to do with generics or template or maybe even metaprogramming, it has very little to do with that. In fact, unfortunately, even though generics and templates are often used with generic programming, they are not nearly powerful enough to express such properties as associativity or something like that. But it's still a very useful technique, and as Alexander Stepanov puts it, generic programming is an approach to programming that focuses on designing algorithms and data structures so that they work in the most general settings without loss of efficiency. In fact, it turns out that many of the fundamental ideas in programming came from mathematics. Learning how these ideas came into being and evolved over time can help you think about software design. And that's pretty much the reason why I put so much emphasis on mathematical ideas. And this is how power function looks like when used for semigroups. And this is how it looks for monoids. And you may wonder, like, okay, why do we need a monoid, and what the hell monoid is? And monoid is just a semigroup with a neutral element. And why do we need neutral element? Well, that's simple, because what do we do when the power is equal to 0? We don't know what to return, right? And monoids, since they have neutral element, allow us to return neutral element for power of 0. So that's why even in Haskell, for example, in S times implementation, you can see that it doesn't support powers of 0. And this implementation supports it, so this is beautiful. Another useful property is commutativity, which basically allows us to reorder the arguments of the operator. And how useful could that be? Well, it's very often used in parallel programming for work stealing or out of order execution. Now we can talk about idempotence. So basically, repetitive application of the operator does not change the result, which is handy when it comes to retries, but that's not only one thing. We can also use it to reduce the long latency tails in distributed settings. For example, when we have massively distributed computation, chances are that one of the nodes are going to be struggling, and because of that we end up with very high latencies for higher percentiles. And to fight that, we can employ speculation. So for example, when we expect one of the computations to get stuck, or we just observe that it's already taking too long, instead of waiting for it to complete, we can launch another computation and then take the result of the computation that finishes first. And this way we can drastically reduce latencies. And now we have all the ingredients to define yet another mathematical object called the semi-lattice. And it's essentially again a set with the least upper bound operator. And that operator has to be commutative, because when we, for example, use gossip algorithm to disseminate information across the nodes, when we deliver those messages, they can come out of order, and we still need to combine them, and that's why we need commutativity. They also have to be associative, again, because we want to combine computations in different orders and also in incremental way. And they also have to be idempotent, because those messages potentially can be delivered multiple times, so we need to have a way to ignore duplicates. And now that we covered all those awesome laws, it would be nice to have a way to just infer them automatically. And there is a tool called quickspec that uses a quick check under the hood to generate random inputs and verify if some of those equational laws hold. Unfortunately, those are obviously just heuristics, so they cannot prove that those laws are true, but they are still very useful to guess them, and then you can use either your judgment or better automatic tools like Agda to prove those properties. And this is, for example, how proof of associativity looks like in Agda. You can also use something like TLA plus to prove maybe more complex properties in parallel or distributed settings. And now we've covered so many relations between simple objects, but we don't have to limit ourselves to just numbers. We can also talk about relations between functions. And this is where Kleisli arrows are super useful because they allow us to compose functions. And to see why it's useful, we can take a look at the compute function. Let's say it's a pure function, so it's also associative, commutative, idempotent. It's beautiful. It's expensive, but since it has all these properties, we can execute it in parallel. We can cache its results, so we can optimize it very well. But at some point, some developer adds a nasty side effect, and all those properties are immediately gone. We can no longer reorder these computations. We cannot use them in parallel setting without synchronization. We no longer can cache them, and it's very sad. But what we can do is we can compute the side effect and return it along with the return value. And this way, Kleisli arrow, since it implements a functional composition, can take care of dealing with these side effects outside of the context of this function. So the function is now again pure. We can cache it, we can compute it in parallel and do all sorts of useful optimizations with it. And Kleisli arrow will victimize itself and deal with all the ugliness of the side effects. This is great. Another super useful concept called functor, and some people may have heard this term in C++ world, but it has absolutely nothing to do with C++. What it is a mapping from one category to another category. And I'm not going to talk about category theory much, but since we've talked about the objects already, the only thing we haven't talked is the morphisms, which are relations or functions between objects of the same category. So functor is the mapping from objects in one category. So we basically map, let's say, all the objects in one set to some objects in another set, but we also have to map the relations between them to the new set as well. And this is how we model world. And for example, we can use this to do all sorts of interesting transformations, like when we need to compare Euclidean distances, we don't have to actually compute those Euclidean distances. We can operate on squares of Euclidean distances. And even though denotationally, in terms of comparison, it's going to be the same, operationally, it's cheaper. Not only that, if our coordinates are all integral values, we do not have to sacrifice the integral domain. We can still stay in it instead of going to the floating point domain when we talk about Euclidean distances because of the square root operator. So it's cheaper and it's also more precise. Great. We can also do a similar trick using logarithmic properties, where instead of using multiplication, we can use addition using the product tool. But you have to be careful. You have to actually measure and see if this gives you a speed up. For example, in my example, in my instance, I didn't get an improvement. In fact, it was a regression. It's also very useful in terms of representing a state. So for example, when, let's say, we have a random vector and we would like to perform some operations, like for example, we want to double all the elements in the random vector, or divide them, or I don't know, add some value to it. And the good thing is that we do not actually need to perform that operation on all the values, because the average of, let's say, doubling all the inputs is the same as doubling the average of those values. So to represent the vector, instead of storing all the elements, we can just store its mean and then compute the transformations in constant time. This is very handy. So what are the takeaways? First, learn business domain. That's what distinguishes coders from engineers. That's what is extremely useful. That's something that's not going to change most likely as quickly as new technologies, and that's what makes you very valuable to your organization. Leverage mathematics. Hundreds and thousands of years, really smart people have invested in building richness and rigorness of the mathematics, and we can leverage abstract algebra and category theory to do things efficiently. We should also embrace generic programming. Efficient usage of essential properties is the key to code reuse and efficiency. And I highly recommend watching the series of lectures called Programming Conversations by Alexander Stepanov. Those are great. Pretty much anything that you can find with Alexander Stepanov is certainly worth watching. Highly recommend it. Define precise contracts. Vagueness leads to distrust. You've probably seen all sorts of defensive programming techniques where people have to copy the input defensively because they don't know if the input is going to be mutated under the hood. So don't do that. Be very precise about your contracts, and if those contracts are violated, feel free to just do undefined behavior. That's why undefined behavior exists, so leverage it. But this is also the key to efficiency, because clients also can take most advantage of the invariance or post conditions that functions provide. So for example, if you return an output that is sorted, we can use more efficient algorithms like maybe binary search instead of using a linear search. So be very, very explicit about your contracts. And practice craftsmanship. Have fun and take pride in your work. And now it's time for questions. Thank you very much.